The role of algorithms in computing. What are algorithms? Why is the study of algorithms worthwhile? What is the role of algorithms relative to other technologies used in computers? In this chapter, we will answer these questions. Algorithms. Informally, an algorithm is any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. An algorithm is thus a sequence of computational steps that transform the input into the output. We can also view an algorithm as a tool for solving a well-specified computational problem. The statement of the problem specifies in general terms the desired input-output relationship. The algorithm describes a specific computational procedure for achieving that input-output relationship. For example, we might need to sort a sequence of numbers into non-decreasing order. This problem arises frequently in practice and provides fertile ground for introducing many standard design techniques and analysis tools. Here is how we formally define the sorting problem. Input: a sequence of n numbers a1, a2 to an. Output: a permutation reordering a1 dash, a2 dash, etc. till an dash of the input sequence such that a1 dash is less than a2 dash is less than an dash. For example, given the input sequence 31, 41, 59, 26, 41, and 58, a sorting algorithm returns as input the sequence 26, 31, 41, 41, 58, and 59. Here we can see that they have given a set of numbers and each number in the ordered sequence is less than the number next to it. And when 41 reoccurs twice, I'm not sure which is it exactly. Such an input sequence is called an instance of the sorting problem. In general, an instance of a problem consists of the input satisfying whatever constraints are imposed in the problem statement needed to compute a solution to the problem. So my understanding is that there is a computational problem and there is an algorithm. And for that algorithm, we can have many inputs and one input. One input sequence is one instance. Because many programs use it as an intermediate step, sorting is a fundamental operation in computer science. As a result, we have a large number of good sorting algorithms at our disposal. Which algorithm is best for a given application depends on, among other factors, the number of items to be sorted, the extent to which the items are already somewhat sorted, possible restrictions on the item values, the architecture of the computer, and the kind of storage devices to be used, main memory, disks, or even tapes. An algorithm is said to be correct if, for every input instance, it holds with correct output. My understanding here is that if it is correct, it shouldn't stop in between. Once it stops, we need to have the expected result as the output. We say that a correct algorithm solves the given computational problem. An incorrect algorithm might not halt at all on some input instances, or it might halt with an incorrect answer. Contrary to what you might expect, incorrect algorithms can sometimes be useful if we can control their error rate. We shall see an example of an algorithm with an controllable error rate in chapter 31 when we study algorithms for finding large prime numbers. Ordinarily, however, we shall be concerned only with correct algorithms. An algorithm can be specified in English as a computer program or even as a hardware design. The only requirement is that the specification must provide a precise description of the computational procedure to be followed. So we need to have proper steps. It shouldn't be ambiguous, it shouldn't be vague. We need to know what we are doing in order to find a solution. What kind of problems are solved by algorithms? Sorting is by no means the only computational problem for which algorithms have been developed. You probably suspected as much when you saw the size of this book. The author included a joke here. Practical applications of algorithms are ubiquitous and include the following examples. The Human Genome Project has made great progress towards the goals of identifying all 1 lakh genes in human DNA, determining the sequences of 3 billion chemical base pairs that make up human DNA, storing this information in databases, and developing tools for data analysis. Each of these steps requires sophisticated algorithms. Although the solutions to various problems involved are beyond the scope of this book, many methods to solve these biological problems use ideas from several of the chapters in this book, thereby enabling scientists to accomplish tasks while using resources efficiently. The savings are in time, both human and machine, and in money, as more information can be extracted from laboratory techniques. So these are just examples, I guess. They are trying to show us how well the algorithms are used in the real world. The author is trying to get us interested in learning the subject, showing us that even after we learn, we can find its use in these many application areas. The internet enables people all over the world to quickly access and retrieve large amounts of information. With the aid of clever algorithms, sites on the internet are able to manage and manipulate this large volume of data. I mean, yeah, this book was written in 2009 and in 2021, right now, we are able to see how the internet is an essential part of our lives. We see machine learning in almost every Google product that refines the search results according to, and yeah, there are so many things, and all those things are made up of algorithms. Examples of problems that make essential use of algorithms include finding good routes on which data will travel. Techniques for solving such problem appear in chapter 24. We need to go to chapter 24 later, but let us go in order. And using a search engine to quickly find pages on which particular information resides. Related techniques are in chapter 11 and 32. Electronic commerce enables goods and services to be negotiated and exchanged electronically, and it depends on privacy of personal information such as credit card numbers, passwords, and bank statements. The core technologies used in electronic commerce include public key cryptography and digital signatures, which are based on numerical algorithms and number theory. Also, one thing to add here is that cryptocurrencies use the technology of cryptography, and that is where the name cryptocurrency comes from. Manufacturing and other commercial enterprises often need to allocate scarce resources in the most beneficial way. An oil company may wish to know where to place its wells in order to maximize its expected profit. A political candidate may want to determine where to spend money before buying campaign advertising in order to maximize the chances of winning an election. We might think all these are based on people and luck, and but I'm I'm beginning to see everywhere there is maths, everywhere there are algorithms. Let us stay motivated to read the book. An airline may wish to assign crews to flights in the least expensive way possible, making sure that each flight is covered and that government regulations regarding crew scheduling are met. People shouldn't be overworked, right? An internet service provider may wish to determine where to place additional resources in order to serve its customers more effectively. All these are examples of problems that can be solved using linear programming, which we shall study in chapter 29. Although some of the details of these examples are beyond the scope of this book, we do give underlying techniques that apply to these problems and problem areas. We also show how to solve many specific problems, including the following. We are given a roadmap on which the distance between each pair of adjacent intersections is marked, and we wish to determine the shortest route from one intersection to another. The number of possible routes can be huge, even if we disallow routes that cross over themselves. How do we choose which of the all possible routes is the shortest? Here we model the roadmap, which is itself a model of the actual roads as a graph, and we wish to find the shortest path between one vertex to another in the graph. We shall see how to solve this problem. Okay, we need to go to those particular chapters in order to learn these things, but still a long way to go. We are given two ordered sequences of symbols, and we wish to find the longest common subsequence of x and y. This is string subsequence, and such things. Such problems are usually asked in interviews. A subsequence of x is just x with some or possibly all of its elements removed. For example, one subsequence is in order. In order, some elements are removed, some elements are retained. The length of the longest common subsequence of x and y gives one measure of how similar these two sequences are. For example, okay, this comes in DNA strands. They do this gene test to find which country you are from, what is your genetic heritage. Probably this is the technology used. For example, if the two sequences are base pairs in DNA strands, then we might consider them similar if they have a long common subsequence. If X has M symbols and Y has N symbols, then X and Y have 2 power M and 2 power N possible subsequences. Okay, this mathematics is quite simple. What it means is either in this given subsequence A to G, A can either be present or absent. B can either be present or absent. C can either be present or absent. So for every element there is, it can either be present or absent. That place can either be filled or not filled. So for that particular place, you have two choices. And again, when this is filled or not filled, you again have two choices for B. Then again, you have two choices for C. So you multiply two times the number of elements, you get this power, 2 power m elements, and that is how you get this formula. Possible subsequences respectively. And this 2 power m and n also includes the possibility of none of the elements being there or all of the elements being there, which is just the uh, base sequence to begin with. Selecting all possible subsequences of x and y and matching them up could take a prohibitively long time unless m and n are very small. Yeah, 2 powers grow exponentially, so it must take a huge amount of time. We shall see in chapter 15 how to use a general technique known as dynamic programming to solve this problem much more efficiently. We are given a mechanical design in terms of library parts where each part may include instances of other parts, and we need to list the parts in order so that each part appears before any part that uses it. If the design comprises n parts, then there are n factorial possible orders, where n factorial denotes the factorial function. Because the factorial function grows faster than even an exponential function, we cannot feasibly generate each possible order and then verify it within that order each part appears before the parts using it unless we have only a few parts. Okay, this may seem like a silly thing, but when you're seeing something as a human, it is easier for you to see that uh, a car comes before a truck comes before an aeroplane comes before a Boeing 737, or as humans we have natural ability to distinguish, or in this particular case, you need tire before you are manufacturing a car. You can't manufacture a car without a tire and then produce the tire. So that makes sense to us as humans, but how do you check when there are a million parts? How do you check which has to come before which? So yeah, this problem is an instance of topological sorting. I'm excited for this, and we shall see in chapter 22 how to solve this problem efficiently. We are given endpoints on the plane and we wish to find the convex hull of these points. Convex hull is the smallest convex polygon containing all the points. So basically it is like drawing a circle which contains all the points. Intuitively, we can think of each point as being represented by a nail sticking out from the board. A convex hull would be represented by a tight rubber band that surrounds all the nails. Each nail around which the rubber band makes a turn is a vertex of the convex hull. Any of the two power n subsets of the points might be the vertices of the convex hull. Knowing which points are vertices of the convex hull is not quite enough either. Again, here, as a human, it is easier for you to just wrap a rubber band around nails, group of nails, bunch of nails, and it makes sense. But how do you tell it to a computer? There are many choices, therefore, for the vertices of convex hull. These chapters are quite far from where we have begun. We are still in chapter 0, I guess. These lists are far from exhaustive, as you again have probably surmised from the books. but exhibit two characteristics that are common to many interesting algorithm problems. They have many candidate solutions, the overwhelming majority of which do not solve the problem at hand. Finding one that does or one that is best can present quite a challenge. They have practical applications. Of the problems in the above list, finding the shortest path provides the easiest examples. A transportation firm such as a trucking or railroad company has a financial interest in finding shortest path through a road or rail network because taking shorter path results in lower labor and fuel costs. Or a routing node on the internet may need to find the shortest path through the network in order to route a message quickly. Or a person wishing to drive from New York to Boston may want to find driving directions from an appropriate website, or this is basically Google Maps or Apple Maps, or she may use her GPS while driving. Not every problem is solved by algorithms has an easily identified set of candidate solutions. I think they are trying to say that it is not possible to clearly say this algorithm works the best. For example, suppose we are given a set of numerical values representing samples of a signal and we want to compute the discrete Fourier transform of these samples. The discrete Fourier transform converts the time domain to frequency domain, producing a set of numerical coefficients so that we can determine the strength of various frequencies in the sampled signal. In addition to lying at the heart of signal processing, discrete Fourier transforms have application in data compression and multiplying large polynomials and integers. Chapter 30 gives an efficient algorithm fast Fourier transform commonly called as FFT for this problem, and the chapter also sketches out the design of a hardware circuit to compute the FFT. Data structures. This book also contains several data structure. A data structure is a way to store and organize data in order to facilitate access and modifications. Till now, what we read was an algorithm. It takes an input data and it produces the output. But data structure, for the input data, we need to have a way to organize it and access it. No single data structure works well for all purposes, and so it is important to know the strengths and limitations of several of them. Also, we need to note that in order for an algorithm to work, we need to have a data structure. And for data structure, we need to have an algorithm for better processing of the data, so it is all intertwined. Technique. Although you can use this book as a cookbook for algorithms, you may someday encounter a problem for which you cannot readily find a published algorithm. Many of the exercises and problems in this book, for example, this so we need so the exercises given do not have a solution. This book will teach you the techniques of algorithm design and analysis so that you can develop algorithms on your own, so that they give the correct answer and understand their efficiency. Different chapters address different aspects of algorithmic problem solving. So they are trying to say, even if you don't memorize everything given in this book, and even if you memorize everything in the book, you cannot find solution to every problem you encounter in real world life. So instead, what you can concentrate on is trying to learn how to do algorithmic problem solving. Some chapters address specific problems such as finding medians and order statistics in chapter 9, computing minimum spanning trees in chapter 23, and determining a maximum flow in a network in chapter 26. Other chapters, these are all chapters I don't think we need to hard problems. Most of this book is about efficient algorithms. Our usual measure of efficiency is speed, how long an algorithm takes to produce its results. There are some problems, however, for which there is no efficient solution known. Chapter 34 studies an interesting subset of these problems which are known as NP-complete. Why are NP-complete problems interesting? Well, first, although no efficient algorithm for an NP-complete problem has ever been found, nobody has ever proven that an efficient algorithm for one cannot exist. So they haven't found a solution, but they aren't able to prove that there is no solution. So there must exist a solution. In other words, no one knows whether or not an efficient algorithms exist for NP-complete problems. Second, the set of NP-complete problems that has the remarkable property that if an efficient algorithm exists for any one of them, then efficient algorithms exist for all of them. This relationship among the NP-complete problems makes the lack of efficient solution all the more tantalizing. For problem solvers, this is a challenge. and the rewards are amazing. You solve every problem that is categorized under NP complete. Third, several NP complete problems are similar but not identical to problems for which we do know of efficient algorithms. Computer scientists are intrigued by how small a change to the problem statement can cause a big change to the efficiency of the best known algorithm. You should know about NP-complete problems because of some of them arise surprisingly often in real applications. If you are called upon to produce an efficient algorithm for an NP-complete problem, you're likely to spend a lot of time in fruitless search. If you can show that the problem is NP-complete, you can instead spend your time developing an efficient algorithm that gives a good but not the best possible solution. So maybe when we complete this book, we can be able to it should be able to we should be able to categorize problems into what they are. Then we should be able to apply an existing algorithm. And if we are smart enough and the problem is new, we should be able to create a new algorithm which works best for the given problem state. You should know, as a concrete example, consider a delivery company with central depot. Each day it loads up each delivery truck at the depot and sends it around to deliver goods to several addresses. At the end of the day, each truck must end up back at the depot so that it is ready to be loaded for the next day. To reduce costs, the company wants to select an order of delivery stops that yields the lowest overall distance traveled by each truck. So what we can simply say it as a round trip. You take students from each house in a school bus, then you drop them back and return back to school. You start with the school and you end with the school, something similar. This problem is well known as traveling salesman problem and it is NP complete. It has no known efficient algorithm under certain assumptions. However, we know of efficient algorithms that give an overall distance which is not too far from the smallest possible. So under the main point here is that it is NP complete, but under certain assumptions we can make use of the efficient algorithms we already know. Parallelism. For many years we could count on processor clock speeds increasing at a steady rate. Physical limitations present a fundamental roadblock to ever increasing clock speeds. However, because power density increases superlinearly with clock speed, chips run the risk of melting once their clock speeds become high enough. In order to perform more computations per second, therefore, chips are being designed to contain not just one but several processing cores. We can liken these multi-core computers to several sequential computers on a single chip. In other words, they are a type of parallel computer. In order to elicit the best performance from multi-core computers, we need to design algorithms with parallelism in mind. Presents a model for multi-threaded algorithms which take advantage of multiple cores. This model has advantages from a theoretical standpoint and it forms the basis of several successful computer programs, including a championship chess program. Chess programs are, for example, in leeches we have Stockfish, we have Google's AlphaGo. This is also the example for example, in your computers, Intel octa-core processor. Then we have an example exercise. Give a real-world example that requires sorting or